This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Are you a tech-savvy developer with an inquisitive mind? SE Radio has an opening for a new volunteer host to join the team and produce 5 episodes per year. Contact show editor Robert Blumen at robert.blumen@gmail.com for details.
Hello, this is Justin Beyer for Software Engineering Radio, and today I'm speaking with Katharine Jarmul. Katharine is the head of product at DropoutLabs, a company enabling privacy-preserving machine learning, and a passionate and internationally recognized data scientist, programmer, and lecturer. Her work and research focus on privacy, ethics, and security for data science workflows. Previously, she held numerous roles at large companies and startups in the US and Germany, implementing data processing and machine learning systems with a focus on reliability, testability, privacy, and security. She's an author for O'Reilly and a frequent keynote speaker at international software and AI conferences. Welcome to the show, Katharine.
Thanks so much, Justin. I'm really glad to be here.
So on today's show, we're going to be discussing security and privacy in machine learning. Now, we already did an intro episode number 286, into machine learning.
And we also did episode 391 on deep learning.
But before we get started discussing, I just want to go quickly over what kinds of machine learning algorithms exist out there. Supervised learning versus unsupervised learning and deep learning, and how do they all fit together?
Yeah, that's actually an interesting area of research now, considering there's been actually a lot of attention recently on reinforcement learning, which is a totally different ballgame. But the classics are, as you noted, supervised learning, which means, guess what? We already have the data and we have good labels. And labels, another word for labels, is what we're trying to actually learn. And so we can think of this like when we have a group of different pictures, we already know this is a picture of a dog or a cat, and we're trying to train maybe computer vision or some other classifier in order to say, okay, this is a dog, this is a cat. So that's what we would call supervised learning. Unsupervised learning is when we don't have labels or we're not quite sure if the labels we have are correct, so we'd rather do some investigation first. We see this a lot in topics or areas like natural language processing, where we might have a whole bunch of text, but we don't really know what the categories are. So this happens a lot when you're trying to, let's say, classify text and say, what are the different topics in this text? What we might first do is a variety of different types of clustering and other unsupervised analysis in order to get a better idea. And then finally, we have deep learning. Deep learning can actually be either supervised or unsupervised and could actually also help with reinforcement learning as well. And deep learning is kind of what my focus has been on recently at DropoutLabs. So we can definitely get into the details if we're interested. But deep learning, if you've heard of TensorFlow, PyTorch, these are all deep learning libraries. And the advent of deep learning really came about in the 2010, 2011, 2012, when there was a resurgence of quote unquote AI, and computer vision really started making some breakthroughs in the deep learning space. And it has since continued and really enhanced machine learning overall as a field, which I would say is part of why we're having this renaissance, if you will.
Thank you, Katharine. So just to quickly summarize, supervised is our labeled data. We have an idea of what it's going to be. Unsupervised, not as labeled or has no labels whatsoever, so we're not 100% sure what data is what. And then deep learning is the definitely more complicated of the three, where you're using all different kinds of things to build the model and analyze the data.
Yeah, deep learning is, if you've heard the term neural networks. So most folks in computer science, you've heard neural networks. Even 30 years ago, they were around, and now they just work properly. And we just have enough compute to make them work properly. People have really thought through different architectures, and they're trained a little bit differently than what we might call simple machine learning models or shallow machine learning models.
Okay, so they're trained differently than these other types of models that we're having. And then when we're discussing models, is that just essentially the statistical analysis that's being done by whatever the data learning algorithm is?
To some degree, it's like an output of a learning algorithm. So a model is kind of like our end result. From a software perspective, we can think of it as our compiled code, if you will. And this model is really what we end up using when we want to perform tasks later. So usually we'll take some data, we do some feature engineering saying, oh, I think this is really important, or we need to pull together this other data. Then we put it into a machine learning algorithm, whether that's simple or deep, and we train it. Now, that's where the difference lies in simple versus deep. That's where it splits. And deep learning has a slightly more complex and also compute intensive training process. And then finally, at the very end, we get this model. And the model is then we're able to, what we say, query the model. So we're able to ask it to make inferences. We're able to ask it to predict something. We're able to ask it to classify something. And this is often what you're interacting with today when you interact with a quote unquote AI system.
Okay, so the model is essentially what I'm going to query against once I have my product, that I want to know that this login is anomalous or is classified as suspicious if I had something like a risk detection or user login detection system.
Exactly. What we could send is maybe the network data, or we could send some of the other behavioral data. We could ask the machine learning model, is this anomalous or not? And it would turn us back usually a percentage or a yes or no answer. And that's what we use. Sometimes we actually even might use multiple models at once and aggregate their consensus together to make a decision, or use different types of the models to assess what exact type of break-in do we think it is if it did say yes.
So when we have these models that you're sending the data to, how do we generally gather the data that we're going to put into these models that's labeled and used for the training?
Yeah, that really depends on the system. For some people, this is a digitization of files that have existed for decades, right? This is a lot of what we're having in Germany right now, is a process of what is called Digitalisierung, in which companies that have done for decades things mainly on paper or in old systems that are not centralized are moving towards a more centralized model. But then we also have, of course, folks that are actively collecting data with every interaction we have with our cell phones and so on. And so you can see a variety of technologies in here. I believe that we're starting to get more standardized, in which we're starting to use kind of data collection and processing tools that can scale easily, that are deployable in the cloud, that are, able to be repeated, often that are open source. And so I'm not sure if you've had anybody on the podcast to talk about Spark or Kafka or any of these large scale data processing frameworks, but essentially they're great ways that you can collect a lot of data. They're open source, usually Apache-based projects, or often Apache-based projects, and they can take in the data from the numerous endpoints and then aggregate it in some sort of data lakes, databases, data storage that you choose for your data.
Okay, so those open source tools is how I'm going to collect it. So the Apache Kafkas are going to stream the data into a Spark data pool, and then I'll use that data to train my model.
Yeah, a lot of times you're kind of collecting all of that and then doing some sort of training and experimentation from the data science or machine learning team. What's happening more and more is even people are trying to move this real-time data collection into what we call real-time machine learning as well, or real-time updates to the model. However, this is still kind of in its infancy, so a lot might change over time. Some projects where you can see that is, for example, Spark now has Spark ML, which is Spark Machine Learning. And there's numerous other players that are trying to work in the space. I know TFX, which is TensorFlow serving, essentially, that also has some integrations for kind of this more real-time processing pipeline. But the average company usually doesn't really need real-time updates of decisions.
Okay, so in contrast to these open source platforms, I've seen some of the larger providers, I think Google, Amazon, starting to provide these tools like BigQuery and those machine learning tools. How do those differ in the way that the model is accessed and is deployed versus a traditional, Apache Spark deployment that I might have in my data center?
A great question. It's yet to be seen exactly how a lot of these tools will develop in, for example, Google in Google Cloud Platform, Amazon in their AWS cloud, and Azure also has a lot available too, where they say, you know what, you can just send us the data. We're going to process it through these ways. We have some automated processing. There might even be some automated machine learning there. And basically, it's all about what is the level of visibility that you want to have and what is the level of control that you want to have. When you deploy your own Spark cluster, it's a lot more work, but you have full visibility and full control. When you use one of these one-click deploys, you often lose some of that visibility and you definitely lose some of the fine-tuning control. Now, what I would say is for an average company or for a company that's just getting into data science, these are great ways to get started because they don't require you having a bunch of machine learning engineers or people that understand the operations or ML ops, as some people are calling it now. However, if you're a more advanced company and you want a little bit more control and you also want the ability to support a machine learning team that might really want to get in there and tune and optimize the models in specific ways, then you're going to have to figure out maybe where's the line there. Maybe you use data processing like a Spark that's automated, and then maybe you focus on the serving side of the models or the training side of the models to really own yourself.
So I'm going to touch on this a little bit later in the security section with the concepts of the like supply chain attacks with these machine learning models. But things like that is where you're going to see the security issues with these larger cloud providers where you're getting these one-click deployments, correct?
Yeah, it depends on the threat model. So when we think of security, we always, of course, have to think of the threat model. And there's definitely, some different places in the overall pipeline or processing workflow where you should probably test or have visibility that something is wrong is not happening. This also comes up in ethics of machine learning as well, right? When we have a biased model or something like this, then we have to check different parts of the output. So, but definitely, obviously, as with most computing, the more visibility we have, the easier it is for us to debug the problem.
Of course, generally being able to trace your problems does make it a little bit easier. So just moving a little bit into the security aspect of the episode, what kinds of security issues do these ML models generally have? Just in my quick research, looking specifically at an article written by Patrick Hall, it'll be number 1 on the show notes, proposals for model and vulnerability security. He mentioned things like data poisoning attacks, watermark attacks, inversions. Can you give us a little more information on that?
Probably the most popular type of machine learning attack is adversarial examples. This is actually like a really fun part of deep learning research, which is that we can fool deep learning models in particular, but also sometimes other types of simple machine learning models. We can fool them in a certain way to misclassify something, or a good example is to see something that's not there. Probably a lot of folks have seen these examples. I'm happy to share a video. There's one that's really fantastic where the research team printed a 3D turtle, and from every angle, it's classified as a rifle by the top machine learning computer vision models at the time. And so these are really interesting. They're actually helping us understand deep learning a little bit better, and they're providing a lot of research fodder there. So adversarial examples have been really thrown a lot in the news. I think there's a lot of fear around them, especially around something like computer vision for self-driving cars. If we can make a stop sign look like a yield sign, what does it mean? And so there's been a lot of research focused on that. Alternatively, though, we do have these other types of attacks, many of whom have been around for decades now. Batista Biggio actually has a really fantastic survey paper of a bunch of different adversarial and other types of security vulnerabilities of machine learning, where he kind of walks you through from the 90s until today. So I'm happy to also share that. I think it's called Wild Patterns. It's a really fantastic paper. And these poisoning attacks are one of them. So he's done a lot of work and research on these poisoning attacks, even being able to poison biometric data. So even when we think of like face unlock or something like this, he's shown that that can be poisoned over time with daily updates. These could be surreptitious to essentially make your face look different so that I could possibly unlock your phone, for example. So these poisoning attacks are also to be taken seriously. And this is why when we collect data, we need to really make sure that we have verified the source of the data and that we understand the intentions and the way that the data is processed. So data governance, so to speak, is something that we often lack visibility into that's really important for machine learning.
So when we're talking about data poisoning attacks, and I'm definitely going to include those two, the video and the paper that you mentioned in the show notes, but when we're talking about data poisoning attacks, we're talking about someone is inserting intentionally malicious or I guess even biased data into your data pipeline for your model. But could you delve a little bit deeper into these adversarial learning attacks and like where that comes from?
Yeah, totally. So adversarial attacks were first kind of discovered by some researchers at Google who didn't actually, I think, intend to discover this. So they're kind of like, I think the initial paper is called something like Interesting Properties of Neural Networks, which is great. So there's like, I found an interesting thing. Anyways, now it's expanded into a huge field of research. In fact, NIPS, which is a very, very popular deep learning conference, now has almost every year an entire track dedicated to adversarial examples. And the problem lies, there's several problems, but the problem lies in the fact most likely, it's still under active research, but most likely that neural networks are kind of getting bigger and have more weights than they know what to do with. And so what we can do is we can essentially add particularly generated noise. This is not random noise, but we can change certain pixels in certain ways and therefore activate different neurons within the neural network, so to speak. Neurons is probably a bad example of it, but different weights, we can activate different pathways, and this leads to a different decision. So therefore, we can truly, let's say, quote unquote, trick the model into classifying, for example, that turtle as a rifle. Or there's been a lot of attacks where even just one pixel attacks, so just changing one pixel, to us humans, it looks totally the same. But to the neural network, that was exactly the target of attack. There's a few really cool libraries for experimenting with this. I've worked on this as well. I gave a talk at CCC, the Chaos Communication Congress, a few years ago now on adversarial facial recognition. I think it was called Fooling Machine Learning Models for Good. Anyways, but there's a very cool library, open sourced and maintained by Nicholas Papunot and some other Google folks called Clever Hans. And so if you're interested in this, it's in Python. You can play around with it and you can just even experiment and see how different types of attack methods work. By now, because it's been several years, there's hundreds of different types of attack vectors. And this is still very much an active area of research and fully understanding exactly why it happens.
So just to circle back a little bit, I heard you mention manipulating weights to trigger different neural paths. What are you referring to when you say weights? Is that calculated weight based off the model data or calculated weight based on something else?
Yeah, so this gets a little bit into machine learning algorithms. So a lot of times when we train machine learning algorithms, we'll talk about weights and biases. And you could just think of this in the most simple example, we can think of this as a function. And we have a function like a plus 2x. The a would be our bias, right? That's like essentially our starting point, right? The intersection. And then 2 would be our weight for the variable x. And so when we think of neural networks or when we think of deep learning, we have many, many, many different weights and biases in many different layers. And depending on how you architect this, this could be very different from model to model and different from task to task. And so the idea is that by adding this adversarial noise, by making a small change, you could significantly affect whether you reach the path of this particular function or a different function.
So what that makes me think of almost as the other security concept of steganography in a way. I'm hiding data in there that you may not necessarily see, and that hidden data I'm now using to manipulate the model.
Exactly. And a really cool paper that's on this is also using adversarial examples as steganography. So people have hidden, text messages and images and so on and so forth by training these machine learning models and then using adversarial examples to generate this. So it's there's a lot of overlap here in terms of can we make, if you think of it from a programming perspective, it's like, is the program deterministic, or can we make it behave erratically? And so far what we found with machine learning is it's hard for us to say that it's fully deterministic. We can still find ways to make it behave erratically, at least at this point in time.
Yeah, in my research, I was seeing a lot of mention of these adversarial attacks that you're mentioning and the supply chain attacks, but more in the sense of these, I believe they referred to it as models as a service, that like something similar to Google or AWS is providing. Do you have any information on these supply chain attacks and how they might be leveraged?
Yeah, so usually when we think of supply chain attacks, we think of places where people are sharing models. So Model Zoo is an example. There's a few other sites that do this, and anybody can just open source their GitHub code or their model executable and say, okay, I trained this, you can use it for this, that, or the other thing. And what happens there is we have to trust that the model was trained properly. So we have to trust that there wasn't essentially backdoors that were trained into the model as well. And so this has been an active area of research of several researchers I can think of who have studied the ability to upload models to Model Zoo with particular backdoors where when I give a certain input, I'm definitely guaranteed a certain output. And I think that this is what you're referring to with some of these model attacks where the user may be using a pre-trained model trained by somebody else.
That's actually exactly what I'm referring to. So that would be similar to the concept that we used to see long ago of like port knocking, where if I connect to port 510 and 506, all of a sudden SSH will open up. It's that same kind of implanted backdoor concept.
Exactly. Yeah. And this is usually, we could think of what is the incentive for this? Well, the incentive is perhaps if I get cleared, I can commit fraud. So maybe this is a fraud detection model. Maybe this is a model where I get like a certain different decision that allows me down some valuable path in the application itself. You can even think of this. I know that there's some folks working in gaming trying to fight against people using things like machine learning to game the gaming system. So it can be something like this, right? So there's a lot of different places, of course, where we're seeing machine learning turn up. So we should be aware of this idea of, just download a model and it will work fine.
Exactly. It's that same concept as not just trusting the source code you found on GitHub to run your critical application.
Exactly.
So changing gears a little bit here, is there any limit to the types of models that these attacks can be used against? Like, is it limited to just supervised learning, unsupervised? I understand that adversarial is going to be limited to just deep learning.
Yeah. I mean, there's been ways, again, with poisoning attacks and other types of attacks like this, where we can create an adversarial setting in a non-deep learning model. So SVMs and so on and so forth, these can also be quote unquote tricked to behave erratically. But the primary focus has been really in computer vision, where we've seen a lot of advances both in the deep learning space as well as the adversarial space. In terms of supervised versus unsupervised, it wouldn't really matter because usually we're using unsupervised algorithms to try to tell us something about the data that we don't know. So an adversarial attack against an unsupervised system would probably just, get clustered in an odd way or get classified in an odd way, but it wouldn't, we're not asking it to make a decision. We're not asking it for a specific label. And so for the most part, these target supervised models. For example, there's a few different types of attacks. So one would be, I want to show it a picture of a dog, but I want it to be misclassified as a cat. This is called a targeted attack. And then there's also just an untargeted attack, which is a picture of a dog, and I just don't want it to be classified as a dog. So you can see there's different levels of intent and also difficulty there, because obviously making something like an airplane look like a table is going to be a lot harder than other types of objects.
And an attacker, how are they going about doing this? Are they stealing your model out of the data pipeline? Are they just giving you bad models and hope that you download it off one of these sharing sites? How does that go about?
Well, as part of the research, actually, one interesting thing that's been found is you don't actually need the original model. So you can, in the initial papers that worked on this, what they discovered that you could do is you could actually just train kind of your own version of the model. And then you can locally build an attack against your local model. So you would just be running that on your local compute, or you can, of course, rent a cloud instance and do it there. But then attacks that work well against your local model or your, offline model, so to speak, will also usually transfer well to the attack that you want to do. And so there's quite a lot of good black box, we call them black box attacks, because we don't need to see the model in order to attack it. We can just see the inputs and outputs. And so there's a lot of different attacks that utilize this. A few are implemented in the Cleverhunts that I mentioned earlier. But there's also a website, I can't remember the name right now, so I'll have to look it up, where a group of researchers working on this problem have kind of documented all of the different types of attacks and accuracies and whether they require any model access or just black box access.
So when you're referring to black box access, would that be almost the sense that I have access to your API that you query against?
That's correct. Whereas we would say white box is if I can look at the model and investigate the architecture and the weights itself. This is becoming more commonplace as things like the iPhone now have an easy ability to train and ship models directly to the device. And this is also, of course, showing up in other types of IoT and mobile devices where we ship the model directly to the end user, or at least to the edge.
Yeah, so what comes to mind for me, at least, is the security cameras that are able to quickly classify person, dog, car.
Yeah, most likely the model is sitting on that camera, and as we all know, it might be running a Linux that's 4 years old.
Of course, the unpatched kernel. So when we're talking about these different kinds of models and all these different issues, is there a way for me as a data scientist or a machine learning engineer to discover these issues in my model?
Yeah, so I think the first and foremost is just to be aware that there's a lot of different information out there in order to properly validate the security of your machine learning infrastructure. And I think that one of the things that's underutilized is basically just a conversation between security personnel and the data science personnel at a company. That can actually go a long ways, because when I talk about these topics, which is more often sometimes than I'd like to, the biggest problem is I go speak at security conferences and they're like, I don't know about this machine learning thing. And then I go talk at machine learning conferences and they're like, security, that's for like the IT guys, right? And for this reason, I think that the biggest problem there is that we need to see the communities come together, form some similar language around this, and have conversations. I don't want the average machine learning engineer to need to know everything about security, neither the average security person to learn everything about machine learning, but we need to have a conversation there. I would say that's first and foremost. And secondly, even just choosing a fun hackathon project and see how easy would it be to poison your data pipeline? How easy would it be to attack one of the models that you have deployed? Give it, time box it, have the team run for 48 hours on it and see what you're able to come up with. Perhaps you'll find some vulnerabilities there if you actually, for example, to use some security language, red team your own system and see what might be there.
So it all comes back to the concept of protect your systems that are handling all of your data and your models, and be aware that the data you're getting into your model isn't necessarily trusted unless you've vetted it outside of that system.
Yeah, there's definitely also techniques you can use, right? So when you're testing incoming data, you should validate that it has the distributions you think it should have. You should validate that it has the types of input you would expect, the values you would expect. So testing data pipelines is something I've been passionate about for numerous years. And I think there's a lot of cool tools and libraries now for doing that. And additionally, so not only testing the data input, but doing some exploratory data analysis before you start training your model and really looking for potential issues in the model training process itself. There's also been a lot of advancements. If you're in particular worried about adversarial attacks, there's also been a lot of advancements in how one might prevent those in, let's say, a production level environment. One of those is around, a great paper was around essentially feature space reduction, dimensionality reduction, and then querying essentially this reduced feature space versus the full adversarial example. If you get two very different responses, then you know that there must be some noisy input there. Now, that could just be like a bad photo, like a fuzzy photo, but it could also be an adversarial example. And there's other ways to protect your APIs or your models itself. There's actually been some huge advancements in training models on what we would call adversarial training. So where essentially as part of the training, you're actually showing a lot of adversarial examples. The problem right now with those is the depth of the model that you need to still score accurately on the real data and the adversarial data. So far, I've only seen papers from Google that can prove this works because it's so many gigabytes and terabytes even, I think, of size for some of these models. But, we've been there before and we got through it and figured out ways to make them smaller. So I'm hopeful that there's a lot of really smart people working on this problem, and we'll continue to experiment and find fun examples and hopefully also find ways that we can better train models in a secure manner.
Hopefully, as machine learning grows, this definitely becomes more of a concern. So I heard you mention APIs in there. When you're discussing that, are we talking about preventing essentially the threat of me trying to guess how your model works by providing it large amounts of input data to almost try to replicate it on my side and rebuild your model?
Yes. In fact, Florian Tramer, who has been a continuous contributor to the security and machine learning space, was actually able to show, I think he presented at Usenix several years ago, was able to show that you could properly steal a model off one of these machine learning as a service platforms with a limited number of requests. And so not only do we have this adversarial example problem where a person might be able to come up with an adversarial example and use it against the service, but a person might actually even be able to steal the model itself to some degree. That's why machine learning API endpoints should be treated just like any other API endpoint of your system. In fact, it should be treated, in my opinion, like an API endpoint of a database. And it should be monitored, and it should be audited, and it should be logged to some degree. And the less public facing you can make it in order to avoid these types of attacks, the better. Now, of course, we want to be able to use machine learning in production. So it's about architecting that in a useful way with some sort of validation and logging of those incoming requests. And if we see abusive behavior, like let's say, 1,000 requests from a particular IP address or from a particular type of user per day, then we might worry about that person or user.
That makes sense. We had done an episode 383 on securing your API with Neil Madden, and they discussed things like rate limiting and appropriate authentication and detection of anomalous API activity. So you're saying applying basic API security would help prevent the theft of a model through an API?
Yes, definitely. And, I think, again, the most important thing always with thinking about security is to think about what is the threat model that you're trying to protect against. So just having that conversation and having, I would say, a proactive approach to security is really important to get the team on. But shutting down your APIs or obfuscating them in different ways and protecting them in different ways is a useful initial step. Then I think you can go from there and you can build on that as an initial platform.
So changing gears a little bit, let's start talking a little bit about privacy. Since we've discussed a lot about the security of your model, let's move into this. So what kind of privacy concerns exist when we're talking about these machine learning models?
What type of privacy concerns do not exist? When I mentioned earlier, there's some data collection that can collect, every movement from your phone and your location, and what you're typing and all of these other things, right? There was just, not to too much date this report, but there was just a whole expose about Uber releasing the feature where you could have maybe one-way recordings of rides and so on and so forth in the name of security, right? But where does this stand in the name of privacy, and who can give consent to that? I have the benefit and ability to live in Germany, which is a very privacy aware society, I would say. And for this reason, there's a lot of really interesting debates happening in Germany and also the rest of Europe around what does privacy mean in an age of machine learning, where most folks in the industry are saying, well, what we need is actually more data so we can train better models. And yet humans still have some right to privacy. And so the cool thing is we're seeing some developments in this, which is what I'm working on with the folks at DropoutLabs. And I'm pretty excited about seeing how the future of privacy and security really in the space of machine learning, how that can coexist in a future.
Definitely. And we are going to discuss a little bit later on how we're mitigating some of these issues around privacy. But just to dive a little bit deeper, you mentioned it's mostly around the data collection issues with the amount of data we're gathering to train a model. What specific attacks exist to breach privacy?
Yes. So similar to kind of how we can think of adversarial examples, and we think of these millions, sometimes billions of different functions that we're using in these deep learning models, we can also exploit this to leak information. And so when we have something like information leakage or the ability to extract some information from some of these models, it often relates to the training data that was seen. And there's been a few different amazing papers and moving forward of the research. There is a particular type of attack called a model inference attack that was developed by Professor Reza Shokri, who's now leading a team that investigates these types of privacy attacks at the University of Singapore. And their work has been really fantastic in moving this forward. Now, how a membership inference attack operates is the ability to determine when I show you sometimes even incomplete information about a person to determine whether they were a part of the training data set or not with very high accuracy. And the problem that we have there is that we've begun to hyper segment our machine learning models incredibly. So a lot of times when we think of a targeted advertisement, I may find a user group or a model that was trained specifically on like your type of demographic that has, something to do with your salary or with your background, even with your gender identity or with your sexuality, these types of things. And therefore, knowing that you are a part of that data set means I can already infer certain things about you and the statistics of the other persons in the group with you. So these types of similarities between the group. In addition, there's also been model inversion attacks against computer vision models where you can actually take a facial recognition model and extract an image that looks quite similar to the face from these attacks. And there was recently also something called an exposure attack against natural language processing models, where they were able to show, for example, training on a bunch of different email data, that they could then prompt it to say, my social security number is, and then extract the most probable social security number. So there's a lot of different things to worry about here in terms of if we're just going to feed a bunch of sensitive information, especially into deep learning models, which we want to use because they're more performant, then we really need to start thinking about privacy protections early on.
So essentially these privacy attacks against these models is all around getting data back out when it wasn't really intended to ever be taken back out and was instead intended to be used from an abstract level.
Exactly. And this has, really changed, I think, especially for folks working within this space, it's really changed the ability or the thinking around this, because we kind of always thought, oh yeah, we just put the data in it and then it's in this model. That's fine. We're only going to use the model for making predictions or classifications and so on and so forth. But when you really think about it, the model is kind of almost like a database. It's some versioning of the data that is stored in order to make predictions. And so for this reason, we really have to treat it, again, a little bit more like a data storage and a little bit less like just some piece of software.
So I had read about these other types of attacks. I don't know if you mentioned it, de-anonymization attacks. How does that fit in with these model inversion attacks?
So these de-anonymization attacks, or we might even call them re-identification attacks, these are often against data sets that were released publicly. So we've had a few of those that have been really famous over time. LaTanya Sweeney did one against the governor when he had passed an electronic health records, like a publication of Electronic Health Records Act in Massachusetts, and she was able to mail some of his records to his house. Because she was able to attack it by connecting it with some census and voting information. So these are usually with publicly released data, not with machine learning models themselves. But it's important to bring up because a lot of machine learning models, or what has been talked about recently, a lot of them are trained on what we would call public data sets, but that were collected maybe under auspicious means. And so, for example, one of the large computer vision data sets called Faces in the Wild was collected from Flickr. And not all of those users, I mean, they had Creative Commons open license. So yes, technically, legally, we can use it. But do those people know? Should we ask for consent? What does it mean when we have all of these open data sets that we use for machine learning? And it's not quite sure, it's very murky, I would say, the level of consent that was given to use them. And so it is important in the machine learning community right now to discuss, do we know how the data set was collected? Do we know what level of consent was given? Do we give the people the ability to opt out or say, please, I was fine with it earlier, but I would like to remove my face now from this training data set? These are all still probably more ethical questions, but I would say big questions within the field of machine learning.
So when we're talking about these de-anonymization attacks, it's surrounding the actual data prior to it being brought in the pipeline. And we're discussing really the ethical concerns around whether we can actually use this data and whether the users understood what they were really consenting to.
Yeah, that's actually a great distinction to make. So usually when we think of de-anonymization in a big data space, we're actually thinking of taking this data set and really being able to re-identify certain individuals in the data set, or maybe even large groups of individuals in the data set. One great example of this was the Netflix Prize, and a paper that came out of it written by Arvind Narayanan and Vitaly Shmantikov is around this de-anonymization. So Netflix said, oh, we have this anonymized data set. You can win $1 kajillion if you figure out how to beat our recommender. They were running this prize, and these researchers said, well, how anonymous is it really? And they started looking into it. It's really fantastic paper, and both of them have gone on to be fantastic contributors to the idea of privacy. But the paper itself basically takes some simple statistical attacks, is able to show an oversampling of certain users, and then they were able to link it to the IMDb reviews of that user. So usually people that reviewed it on Netflix, within a few days, they would review the same movie on IMDb, and they were able to, I believe, re-identify something like 15 to 20% of the so-called anonymized users in the data set, which is pretty crazy when you think about it, especially back then in 2006. So we've only gotten more data personally available online when you think of something like IMDb. Can I link data to something you posted on Facebook publicly? Can I link data to something you posted on another social media site? Can I link it to something in your LinkedIn? Can I link it to something on any number of sites where people publicly store information? And from a privacy perspective, also to some degree from a security perspective, when we think about, do you know who knows what about you? This is, a huge concern. I think secondary to that, and kind of what I went off on tangentially, was also the idea of privacy in machine learning concerns, which is, do we actually have the right consent for the data that we're using on a daily basis for machine learning? And as a user of machine learning, as well as a maker of machine learning for myself, my concern is, do I know what data is being collected and used for machine learning? And do I have a say over this to some degree? And I think that's currently a big debate within industry and also within regulators across the world right now.
So essentially the correlation is the attack that they made with the Netflix data. Essentially, they took Netflix data that wasn't supposed to be linkable to anything and were able to correlate user one reviewed movies A, C, and D, and a similar person over here on IMDb reviewed these movies around the same time. Therefore, these are probably the same person. And the concern would be that I could then expand that outside of just IMDb and Netflix, or leverage IMDb data to then expand that further and almost build a large web or network of nodes to gather more information on this user.
Yes, exactly. I think as a part of the paper, they were actually able to uncover one. It was either somebody they knew in their friend circle or something like this, and they were able to say, were these your Netflix reviews? And indeed, it was a match. So it was similar ratings, similar time span, and the same movie. And a lot of times on sites like IMDb, people use their real names. So it went from Netflix saying a totally anonymized data set, we're releasing it, to, oh, I can link this to a human. And the concern there is people say, well, whatever, I talk about movies online, what big of a deal, or like it's not a big deal. But what if it was a particular political movie? What if it was also informed by, let's say, the user's sexual preference or other political identity, so on and so forth? And so this is where the benefit of having something like privacy and the benefit of really what humans think of as privacy, which is not, oh, I posted it to Facebook, therefore the world must know it. Humans tend to think of privacy in form of trust. When the average person is asked, even if they have public settings on Facebook, who's reading your Facebook, they think my friends and family. They don't think my friends and family and this machine learning researcher that's using it to make Cambridge Analytica profiles, So I think we have to kind of have some empathy for the user and not say, oh, well, it's their fault because they didn't have the perfect privacy settings. Well, unless we make the perfect privacy settings the default, we all know that default passwords, default settings don't work. So we maybe have to make better defaults, which is some of the cool stuff happening, or the conversation happening in Europe right now after GDPR, of what we would call private by design. So can we build secure and safe and private defaults and then say, you want to go in there, you want to change it and make everything public? Sure. But you took an active action. You didn't just have it happen to you.
Exactly. And to link it back to security, we usually hear the discussion of secure by default. We're deploying something that, isn't running a Linux kernel that's 10 years behind and has 15 known vulnerabilities. Instead, we're deploying an up-to-date version and planning to keep it up to date. And just a little more on the privacy side of that, I also link it back to the concept of a social engineering email. These things that I may not have intended a random person on the internet to know, when that gets used against me in a targeted attack of some kind, I wouldn't necessarily expect that, oh, it was a machine learning algorithm that figured out what my preferences are and is now crafting these phishing emails against my corporate email and using it as an attack against my company.
Exactly. And we're seeing some more sophisticated phishing emails that some researchers believe are indeed being used or being at least targeted by larger data collection from a variety of public websites, as well as maybe even natural language generation to use different types of linguistic choices to make that person more susceptible to open or click on the email.
That definitely would be a serious concern, and I can see how leveraging machine learning in that context would be beneficial to an attacker. So switching gears just a little more, let's actually talk about how we can resolve some of these issues around privacy and machine learning. Researching a little bit, it'll be number 4 in the show notes, privacy preserving machine learning, threats and solutions. They talked a lot about this privacy preserving machine learning, PPML. Would you be able to give us some more detail on that?
Yeah, privacy preserving machine learning is a little bit of a large field right now because there's a few different ways to approach the problem. One of the ways that we can think of privacy preserving machine learning is that during the training process, can we figure out different methods that can be used to protect privacy? One of the ways that we could do this perhaps is by adding what we call differential privacy, or by using differential privacy techniques during the training. For example, there is Google's open source differential privacy library. There's also TF privacy for TensorFlow privacy. These are some ways that people are experimenting with adding differential privacy techniques to machine learning. But the problem, differential privacy is fantastic. It's a great way of thinking about privacy. It allows us to try kind of quantify privacy loss. So we're able to say, hey, you and your data, we're going to quantify your loss over time. And the goal is eventually, when we have reached the end of the amount of information we will use for you, that we never use your data again. But the issue there, too, is that if we have too little information about any one person, then adding noise, which is what we normally do, we add some disruption to the data. We might even suppress certain records. If we do this too much, then we also lose a lot of accuracy. So it's important to think, when you think of something like differential privacy, is what is the best protection for the users that I have, and also that's going to allow me to still train an accurate model to some degree. And this is really where the space that, for example, DropoutLabs has been working on, and we've been thinking about collaborating also with TensorFlow Federated in this space, because encrypted learning and federated learning are different approaches to this problem that protect against different types of privacy threats. I can go further into those if they're of interest. I'm not sure if they were described as well in this PPML, or privacy preserving machine learning paper.
So we can circle back to those. I just wanted to cover, they had mentioned garbled circuits in there. Is that a type of machine learning privacy protection?
Yes, indeed. Yeah, garbled circuits, I would say, is a lot closer to kind of the encrypted machine learning that I've been working on, and that the team has been working on for some time. So I'm less deeply familiar with garbled circuits, but I do know that they're utilized in similar ways as encrypted, for example, homomorphic encryption, as well as secure multiparty computation for encryption.
Let's actually delve into those a little bit more. When you mentioned homomorphic encryption, how does that work? I've definitely heard about it outside of just machine learning, just in a general data privacy context.
Yeah, so homomorphic encryption was presented in theory, I believe, in the 70s, the idea that this could exist. But it wasn't actually proven, I think, until a decade later. And it has a few different varietals. So there's partially homomorphic, fully homomorphic. But the idea of homomorphic encryption overall is that you have digits. Let's say you have a 5 and a 2. And if you take a homomorphically encrypted 5 and a homomorphically encrypted 2, these are encrypted using usually some sort of private key protocol, then you're able to add those together and decrypt them then and get a 7. So the idea is, can we perform computations in an encrypted way and still get the correct mathematical answers? And so the cool thing is that we can now do that. We can do that for numerous mathematical computations. The issue that we still have with homomorphic encryption is that it's extremely compute heavy. And so when we think of a machine learning problem, there's just some types of models where we're adding a 10,000 time difference in compute, maybe even more than that for some models. And again, when we think of something like deep learning, it's very difficult because these have many, many, many computations, which is why the team at Dropout Labs has been working on secure multi-party computation as an alternative to homomorphic encryption, which is a different type of, we could say, a secure encryption and compute environment than homomorphic encryption.
So you mentioned the secure multi-part encryption. Can you delve a little bit more into that?
Yes, yeah, definitely. It's actually somewhat new to me. The team has been actively researching this for 2 years. And Morten Dahl, who's our head of cryptography, is really a fantastic contributor within the space. But secure multi-party computation is the idea that if we have some level of trust amongst us, but we're worried about, let's say, the curiosity of the people that we want to run a particular computation with, then secure multi-party computation is actually a fantastic solution. So the idea is that we have mathematical ways of sharing computation amongst many parties. You might have heard of the concept of something like zero knowledge proofs. This touches on the same space of computing. And it's the idea that can we share little pieces of information, none of which would actually show the numbers that I hold, but can we then resolve a mathematical problem together where we can all get the answer? So if you had a 5, I had a 2, and somebody else had a 1, we wanted to add them all together. At the end, we would get 8, but we would not know who had what numbers. And of course, this can scale to many, many different parties. And so this is really useful when we think of machine learning because we can now also think about keeping data away from a central repository. So when we think of secure multi-party computation, we can also start thinking of, well, could we do this in what is called a federated setting? And the folks at Google have done a lot of contributions to what's called federated learning. There's also other folks that are working on this. But it's the idea that the data can stay on device or stay on a single computer. So essentially that on your phone, the data could stay there. Then the machine learning model would be trained in a centralized way, but just small updates from each device. Now, the issue with that is it may leak some private information because let's say your update is very, very specific to your interests. One way that we can get around this is by allowing us to do those updates in an encrypted way using this multi-party computation. And so that's been kind of an active area of research and work for the team is how can we, enable people to keep data closer or maybe to share less data, minimally for industry partners to share less data, but to still compute a machine learning model together that's also therefore more secure and more private because the inputs have been encrypted.
That definitely makes sense. The zero knowledge proofs I've only heard really in the context of, in fear of using too many buzzwords in this talk, blockchain concepts. I have not heard of it in the machine learning context yet. Is there a difference in how the zero knowledge proofs are implemented in something like a blockchain versus a machine learning, or is it the same concept?
So zero knowledge proofs, I just said as an example, as something that somebody might have heard of, because I know blockchain has, a good marketing campaign behind it to explain. It's just one form of secure multi-party computation. And so it's interesting. There is some overlap there in terms of how do we think about protocols between the different, they're often called players in the game. So how do we securely send the information and aggregate that in a useful way? And this overlaps very, very much with the secure multi-party computation in something like machine learning. So there is some synergy there, to use a good word for you.
So how does this fit into the realm of the different anonymization versus pseudo-anonymization techniques realm of handling your data?
Yeah, that's a great question. So, there's so many different active areas of research right now on how we should approach a lot of these. That's hard to say that we have a one size fits all problem here. It's good to kind of get an idea of the space. And again, to start with, what is the actual privacy threat that you're worried about? If you're releasing a data set into the public, you should be extremely worried about being able to properly anonymize that. That's going to be very difficult, and you should look at things like differential privacy. You should look at things like anonymization, and you should even just consider, what do I actually want to get out of releasing this data set, and what is the level of risk that I'm willing to take against the individual privacy. But when we look at something like machine learning, where again, we're not releasing the full data set, so we are probably thinking of a different type of privacy attack. Maybe we're worried about, maybe we need to buy data from somebody else, or we need to share data with somebody else to make a model. Then we have to be worried about the privacy of the people that entrusted us with their data, right? Do we really want to give up a bunch of user data just to get a better fraud model? Maybe we do, but can we do so in a privacy preserving way? This is where a secure MPC would come in, or something like TF encrypted, which is what the team has been working on. But there might also be other privacy concerns. Are we using personal data to train facial recognition? Then we should think about, can we protect the API against attack? Where is the model going to live? Can we make sure that the model is trained in a secure environment that was, properly locked down, so that nobody was able to steal the images from just our open Amazon cloud, this, that, and so forth. So this is why I think there's a lot of overlap when we think of something like machine learning between privacy concerns and security concerns, because we also have to think of, if the data that we're using is sensitive data, if it's personal data in any way, shape, or form, we also have to take the right security measures to make sure that we're creating a training environment that is absolutely privacy preserving, but also extremely secure.
So essentially, it all comes down to classifying your data appropriately and applying appropriate security controls around it to prevent these privacy issues as a result of a data breach.
Yes, yeah. I think probably the primary concern that most folks should be worried about, and maybe are less, is that somewhere in their machine learning pipeline or workflow, they have left some things open, or they haven't assigned right groups, or anybody at the company can access this particular database. That's, of course, the largest concerns when we think about these issues. Of course, it's also, I'm happy to nerd out about the most, intricate of attacks, but I always like to think about the XKCD comic, where it's like, oh yeah, they're going to break into my computer because I didn't use a proper key size. And it's actually just like that. They're going to break your fingers and make you give up your password. So you always got to think of the simplest attack first, and then move to the advanced. And I think there's a really strong, cool future in an idea of a differentially private, encrypted, federated setting for machine learning. But maybe that the extreme goal, maybe the first goal is, have we properly locked down our APIs and checked all of our pipelines to make sure that they're doing what we expect they should do.
Fantastic. So just to start to wrap up the show here, is there anything that I missed that you think a developer or a software engineer should know?
Oh, that is a hard question. I think that developers and software engineers should know that the machine learning as a service, although it's really great to be able to just like one click train a model, that often those are not optimized in a lot of ways. And so we should be a little bit wary that when we think about security and privacy, that they're the optimal solution. I'm all for the people getting acquainted with machine learning in that way. Just think about, do you want to deploy that? Is that going to be the first thing that you want to deploy? And if so, to ensure that you're taking the right concerns or protections against the type of data that you're putting into it and the API endpoints that are going out of it. So just, take some time to get to know your data. You don't have to be a data scientist. A lot of these services have different ways that you can view the data that's there. They can search through the data that's there. So just try and make sure that, if people's names and ages are going into it, that there's a reason for that. Just basically start asking yourself the question. I like to say it's the mom test. If you wouldn't want to do that to your mom's data, then you shouldn't do it to the user data that you've been entrusted with.
Exactly. So collect the data that you need, not just the data that you want. And if you're going to use it, make sure you actually have a legitimate business case for that usage.
Exactly. Data minimization is the fancy word for that. But I think it's a rule we can all live by.
So where can our listeners follow you at if they want to learn more or spark a debate with you?
Sure. You can find me on Twitter. I'm at KJAM, KJAM. Or you can drop me a line at Katharine@DropoutLabs.com, and I'm happy to chat about the cool stuff the team is working on.
Thank you, Katharine. I'll make sure to include those in the show notes. So I just want to thank you for coming on the show and discussing how we can secure our machine learning models and pipelines. This is Justin Beyer for Software Engineering Radio, and thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.